Hello, welcome back to the YouTube channel. So today we are met by one of the many big bad wolves of integration. Today we will be integrating 1 over x to the power of x dx with the bounds between 0 and 1. Now this question is deemed impossible by many, and by some deemed very difficult using very random theorems. Now I will show you that it's actually simple once you take a good look at the question. Now this is the type of question a math teacher or professor would give to that one arrogant or cocky calculus student. You know, that one student that goes, "Oh, I could integrate anything, I could differentiate anything, whatever you give me I will solve within the matter of minutes." Right? And then the professor or math teacher says, "Well, why don't you integrate 1 over x to the power of x dx?" And they're stumped. They don't know what to do. Well, I'm going to show you what you're meant to do, what you can do. Now, if these bounds were not between 0 and 1, this question would be impossible, at least for me, after what I've explored. Okay? So, let's go to it. Right? Let me go over here. Now what most would do, how most would tackle this, at least at the start, is do U substitution. But that's not going to work out. Matter of fact, let me show you what happens when you do U substitution. Right? So let's let U equal 1 over x to the power of x, which is also equal to x to the power of negative x. Right? Pretty simple so far. So let's take the ln of both sides. So ln u is equal to negative x ln x. Now let's differentiate both sides, right? So this will become 1 over u du, and it will equal, here we have to use the product rule, which means let's differentiate the first, keep the second, and let's put the negative on the outside. So differentiate the first, keep the second, that will leave us with ln x, and we add, now we keep the first and differentiate the second, which will just give us 1, because x multiplied by 1 over x is just 1. And let's do dx. Now here is where we get stumped. We cannot express this in terms of u, which we need to, so that we can make dx the subject and substitute it into here when we do u substitution. However, we cannot express this in terms of u. This is where most get stumped, give up, and call the question impossible. However, I will show you that it's not impossible, right? Now, this is the type of question where you either drown in the deep or rise from it. So we have to use every single little ratty trick that we know, every theorem, everything, until we figure out what the key to this question is. So let me erase everything. And let's say I is equal to our integral, which is from 0 to 1 of 1 over x to the power of x dx. Now we already said that x to the power of 1 over x to the power of x can be expressed as x to the power of negative x. Now what if we represent this in terms of e and ln? So we can actually take the ln of this and put it all as a power of e, because e and ln cancel each other. Now we know from the rules of log and ln that we can take the exponential and put it as a coefficient of ln x. So let's take the exponent and put negative x over here, right? So we can actually express this like this. So let's actually do that really quickly. So let me erase this. Let me put which is equal to the integration from 0 to 1 of e to the power of negative x ln x, and let's put a dx over here. Okay, now what do we do? Let me give you a second for you to think about what we can do here. What's the next logical step? Okay, let's go over to this board over here, because I want to remind you of something. So let's put a note over here. Note. Using the Taylor series, we can express e to the x as the sum from n equals 0 to infinity of x to the power of n over n factorial. That's how we represent e to the power of something in the Taylor series. Okay, so let's actually do that over here. So e to the power of negative x ln x is the same as the sum from n equals 0 to infinity of negative x ln x all to the power of n over n factorial. Correct? So let's actually put that over here. Okay. So we can equate this to the integral from 0 to 1 of the sum from n equals 0 to infinity of negative x ln x all to the power of n over n factorial dx. Now, what's the next step? What can we do here? How do we manipulate this to get rid of that integral? Now, we notice that this function diverges, and the reason, converges. This function converges. Now, the reason it converges is because x is between the bounds of 0 and 1. X is between 0 and 1, meaning this entire thing will converge at some point. Okay? Now, remember at the start, I said if the bounds weren't between 0 and 1, and let's say they were from like 0 to infinity, this would diverge, meaning we cannot use the next thing that we're about to use. So, using the dominant convergence theorem, we can actually interchange the integral function and the sum function. Okay, so that's using the dominant convergence theorem. So let's do that really quickly. See, if this diverged, we would not be able to do this. That's why I said if we didn't have those bounds, I would not be able to solve it. Okay, now I don't like this n factorial. I don't want this to be inside our integral, and matter of fact, I don't even want it to be in our final solution. But we'll get to that later. So we can actually take this out as a constant, and let me just do that real quickly. So we can say that this entire function inside the integral is equal to negative 1 all to the power of n over n factorial multiplied by x to the power of n multiplied by ln x to the power of n. Right? This is the same as saying this. So let's do that here, and this is a constant which is inside the integral, and the integral only wants whatever has x in it to be inside. So we can take that constant outside and keep it with the summation. So let's do that really quickly. I'll write a new line here. Which is equal to the sum from n equals 0 to infinity of negative 1 all to the power of n over n factorial times the integral from 0 to 1 of x to the power of n multiplied by ln x all to the power of n dx. Okay? This is our new thing. Now remember, I said we don't want that n factorial in our final answer. So we want to get rid of this integral and the n factorial. Now we can actually, we can knock down two birds with one stone. And I'll show you how right now. So let's go back to the small board over here. Let's keep that note because we're about to make a new note. Now we know that n factorial is equal to the gamma function of n plus 1. And this is equal to the integral from 0 to infinity of, let's say, t. Okay? T to the power of n multiplied by e to the power of negative t dt. Where t is just a normal variable. T is just a normal variable. I just said t. It could be x, could be u, could be y, could be whatever you want. So, we want this integral to look like this, so we can equate it to n factorial, which will also get rid of this n factorial. Now, how could we do that? Let's take it step by step. What if we do a u substitution, right? What if we do a u substitution? Now, what would our u equal? Should we use u? Let's use k. Let's use k. Let k equal, let's say ln x. That means our bounds will change. So when when x is 0, k is negative infinity. But we actually want infinity, not negative infinity. So let's let k equal negative ln x. How about that? Yeah, that sounds good. That sounds good. Because when x equals 0, then the bottom bound will turn into infinity, because k will equal infinity. And when x equals 1, k will equal 0. Now we will deal with flipping the bounds later on, so we can equate it to this later on. We'll do this later on. Now, if this is this, so I want to actually let x be the subject here. So let's say, yeah, so e to the power of negative k is equal to x. Now we want dk and dx. So dk is equal to negative 1 over x dx. Now we want to make x the subject, don't we? I mean dx the subject, don't we? And we know that x is equal to e to the power of negative k. So we have, yeah, okay, so that means, yeah, so we have, okay, so that means that dx is equal to negative e to the power of negative k. Yep. So let's actually do our k substitution now. So let me just erase this to create some space. So this is equal to the sum from n equals 0 to infinity of negative 1 all to the power of n over n factorial multiplied by the integral. So we changed the bounds. We said that when x equals 0, k will equal infinity. So from infinity, and when x equals 1, k will equal 0. So from infinity to 0. Of what? So remember, we said that x equals e to the power of negative k. Didn't we say that? So let's do e to the power of negative k. Negative k to the power of n is just negative k n. So we can write that, right? And now let's multiply this. Now remember, we said that negative t is equal to ln x. So we can, or negative k, sorry, negative k. So let's write this as negative k to the power all to the power of n. Let me erase this over here. So we have dx is equal to negative e to the power of negative k. So let's just memorize that really quickly. Actually, we don't even need to memorize. We're about to write it right now. So multiplied by negative e to the power of negative k dk. Okay, now what? What do we do now? We can take this negative 1 as a constant outside, negative 1 to the power of n, and multiply this by this, so this becomes a 1. And this negative over here, we can actually use to flip the bounds. And I'll show you that right now. I'll show you that pretty soon. Okay, so let's start writing stuff up here. So let me just create a line over here. Okay, so we can take this negative 1 out, because negative k all to the power of n is the same as saying negative 1 to the power of n multiplied by k to the power of n. And we can take this negative 1 to the power of n outside because it does not have k in it, and this integral only wants to keep what has k inside. And then we have negative 1 to the power of n multiplied by negative 1 to the power of n, which will just leave us with 1 to the power of something, and 1 to the power of anything is just 1. So we can actually write this as 1 now. And this negative will flip our bounds. Now let me show you how. Let me go to our small board over here. Now where is my yellow chalk? Here we go. So let's remember this rule. The integral from a to b of f of x is equal to the negative integral from b to a of f of x. This is a basic integration rule that we know. And this negative will come outside. This negative next to the e can come outside of the integral, meaning we have the negative integral of f of x being this jibber jabber, meaning that this negative, we can get rid of it by flipping the bounds. And flipping the bounds will let us come closer to what we need to get n factorial from the gamma function. Isn't that beautiful? Everything works in harmony. Isn't that just amazing? So let's say I is equal to the sum from n equals 0 to infinity of, remember we said that negative 1 to the power of n will turn into a 1. So we say 1 over n factorial multiplied by the integral from 0 to infinity this time. And let's manipulate the inside. So this negative is now gone, meaning we can multiply e by e. They have the same base, and we can combine these powers to get we can get negative k times n plus 1. So we can get the integral of e to the power of negative k times n plus 1, and this is multiplied to negative k to the power of n. Actually, this is multiplied to k. Remember, we got rid of that negative 1. So this is multiplied to k to the power of n, and let's put a dk here. Now, isn't this really close to what the gamma function says? However, this n plus 1 is bothering us. Ew. Let's get rid of that n plus 1. It's a disgusting n plus 1. So let me erase all the left side here. Give me more space to work. And let's put a box around this thing. Okay. So this is where we're at right now. Now how about we do a second u substitution? Well, we're gonna use a different variable. Let's let it be t. Let's let it be t this time, okay? So let's say let t equal okay, let's let our t equal n plus 1 times k. This implies that k is equal to t over n plus 1. Now dt is equal to n plus 1 dk. And this implies that dk is equal to dt over n plus 1. Okay. Let's do this. This is amazing. Okay. So I'll integral here, then I'll write the integral here, then I'll move it to the left side once we can remove all this after doing the t substitution. Okay. So this integral, let's focus on this integral only, turns into the integral. Let's look at the bounds, by the way. Let's see if the bounds change. So when k equals 0, t also equals 0. When k equals infinity, t also equals infinity, meaning our bounds actually don't change. So the integral from 0 to infinity, sorry, that infinity looks more like an 8, I'm sorry about that, but our integral from 0 to infinity of, let's put that k first. So that k turns into t over n plus 1. So here we have t over n plus 1 all to the power of n multiplied by e. That negative k times n plus 1 just turns into negative t. Multiplied by dk, which is equal to dt over n plus 1. And here, it's beginning to look a lot like Christmas. It's beginning to look a lot like what we want it to look like. Let's go back to that small board and write what we want it to look like. Let me remove this. We want this to look like this is what we want it to look like. And we are getting really close. See, we have that t to the n, we have that e to the negative t, we have that dt. We're getting very, very, very close, aren't we now? So, we want to get rid of this n plus 1, this n plus 1, and they are both constants, or they can be both manipulated into constant, because this can be written as 1 over n plus 1 all to the power of n multiplied by t. And this is just dt multiplied by 1 over n plus 1. And 1 over n plus 1 is also a constant. So this is a constant that goes out, and this, it's multiplied by another constant that goes out, which is 1 over n plus 1. Now, can't we simplify this? Can't we say that this is equal to 1 over n plus 1 multiplied by n plus 1? Can't we just say that? We can. So let's actually take those constants out, and let's write our integral much more cleanly on the left side. So let's say I equals the sum, let me put in equals here, from n equals 0 to infinity of 1 over n factorial multiplied by 1 over n plus 1 to the power of n plus 1 multiplied by the integral, this integral, but now it's in the form of this. Let me show you. It's in this form now. From 0 to infinity of t to the n multiplied by e to the negative t dt. And what is this equal? It is equal to n factorial, right? So this is equal to n factorial. So this is equal to the sum from n equals 0 to infinity n factorial divided by n factorial is just 1. So we're just left with 1 over n plus 1 to the power of n plus 1. That's our answer. There we go. The impossible big bad wolf. Integration is done very simply. Come on, you have got to admit that after all that process, it was simple in the end. You just had to try everything, and we have risen from the deep. Remember at the start, this is the type of question where you drown in the deep or rise from it. We have risen from it. We have risen from it. Now, if you computate this to the first x terms, whatever you want, it will be approximate to 0.783 3 dot 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 dot. I believe this is what it's approximate to. Now, there we go. Thank you for watching. I hope you learned something. We have just solved the quote-unquote impossible integration. Thank you for watching. Have a good day.